Hello everyone. In this lecture we will be continuing our discussion in the probability theory, and this lecture will be about continuous random variables. We will discuss the definition of random variables and we will define what is meant by a continuous random variables. Then we will explain the statistical functions that describe continuous random variables, namely the probability density function and the cumulative distribution function. And then we will use those to calculate expectations and moments of continuous random variables. Let's start with the definition of a continuous random variable. Previously, we defined a random variable as mapping between a real number and the outcomes of a random experiment that are the elements of a sample space. And we defined a discrete random variable as a random variable whose range is countable. Either it was finite or infinite, but has a certain pattern that deems it countable. On the other hand, if the range of a random variable is uncountable, that means that our random variable is continuous, because in such cases the mapping between the elements of the sample space and the real number takes almost all the real numbers, or even if it's a range of the real number from a minimum value to a maximum value, any range of real numbers is by definition uncountable, and hence the random variable is a continuous random variable. For example, if we have a copper wire and we estimate the current through this copper wire, and this copper wire is in a circuit with a certain resistance and a certain voltage range, and this resistance is variable, which makes our current a random variable. In this case, the current ranges from a minimum value, I minimum, to I maximum. However, it can take any value in this range. For example, if our current ranges from 0 to 20 milliamperes, that means that the current can take any value from 0 to 20, and as we know, this range is uncountable, and hence the defined random variable is a continuous random variable. Also, if we measure the temperature at any day and we consider a random variable as the value of such temperature, so this temperature ranges from a minimum temperature to a maximum temperature, and it can take all the values between this T minimum and T maximum, which makes it again a continuous random variable because the range is uncountable. Then how we describe a continuous random variable? As we did with discrete random variables, we use statistical description functions. The first of those functions is the probability density function, and we can consider the probability density function as the function that is used similar to the probability mass function in discrete random variables to describe our random variable. However, there are few differences between the probability density function and the probability mass function. Let's first review what we mentioned about the probability mass function. We said that the probability mass function f of x is by definition equals the probability that the random variable takes a specific value x. And to avoid any confusion, let's assume this is f of xi, and this is equivalent by definition to the probability that the random variable x takes a specific value xi. However, in case of continuous random variables, the probability that the random variable takes a specific value xi is equal to 0. Why is that true? Because again, the probability means the likelihood that a certain value or a certain event occurs. So my event here is that the random variable takes a value xi. However, the range of possible values of the random variable x is infinite. So the probability that the random variable takes exactly a single value of that range is infinitesimally small that we consider it equal to 0. So the probability density function will not be equivalent to the probability that x equals xi, because again this probability is equal to 0. However, what probabilities can we calculate if you cannot calculate the probability that a random variable takes a specific value? We can take the probability that we can calculate the probability that a random variable takes a value in a certain range. For example, we can calculate the probability that random variable x takes any value from x1 to x2. This value can be calculated, and the equal sign here does not make any difference if it is there or if it is absent, because again the probability that the random variable x takes value x1 is equal to 0, and the probability that the random variable x takes the value x2 is equal to 0. So we can simply consider that this is equivalent to the probability that x is between x1 and x2, with x1 and x2 excluded, plus the probability that x equals x1 plus the probability that x equal x2. And as we mentioned earlier, these two values are equal to 0. Again, this is different from the case of discrete random variables, because in discrete random variables the probability that x is less than or equal x1 is not equal to the probability that x is less than x1. Again, this is in discrete random variables, because in this term the probability of x1 is excluded, and for any value of a discrete random variable the probability that the random variable takes that specific value is in general non-zero. So what is the definition of the probability density function? It's a function that can be used to give us an estimate about the range of probabilities of a certain random variable. For example, if the CDF is defined as this function, as a function of x, f of x is plotted as this function from 0, for example, to 10, then we can calculate the probability that x is in the range from 3 to 5. Again, it doesn't matter whether 3 and 5 are included in the domain or excluded. And this probability is calculated as the total area under the curve in the specified range from 3 to 5. So this shaded area represents the probability that the random variable x takes a value from 3 to 5. So this is the integral of the probability density function for values of x from 3 to 5. And we can generalize that for any range A to B, where we integrate the probability density function for values of x from A to B. In order to better understand the notion of the probability density function, let's review a simple physical equation which says that the pressure is the force divided by the area. So we can say that the pressure is the density of the force over the area. So if you have fixed force, the pressure changes as the area changes. And if we have the smaller the area, the higher the pressure, although the force is still the same, but now the density of the force over this area became much higher because the area is reduced. So this is what we usually mean by the density. It is the distribution of something based on another variable. So similarly here, the probability density function, it gives us the density of accumulation or the density of likelihood of the random variable in certain ranges. As the range decreases, this probability decreases, and on the other hand, as the range A to B increases, the probability increases. And the rule of total probability here applies. For example, if we calculate the probability that x takes any value from 0 to 10, what will be this probability? Since 0 to 10 is the whole range of the random variable, then this means that the total probability is equal to 1 or 100%, which means that the total area under the curve of the probability density function is equal to 1. This is one of the characteristics or the properties of discrete continuous random variables, is that the total area under the curve of the PDF is equal to 1. Again, because this means this is the total probability or the probability that this random variable takes any value from the whole range, which is definitely a sure or a certain likelihood with a probability of 1. Then, if this is the case, what will be the cumulative distribution function? The cumulative distribution function has the same definition as we defined before. It is the probability. So if we define it as capital F of x, it is the probability that our random variable has a value less than or equal a threshold value xi.
Adding sprinkle bin.
And as we mentioned earlier, this probability was calculated as the integral over the PDF in the specified range. So here, if we consider that, if we want to calculate the probability that a random variable x is less than or equal xi, so that means that the upper limit is xi and the lower limit is the minimum value of x, or in general, to keep the definition general, this minimum value can be as low as negative infinity. Then what is the definition between the probability density function and the cumulative distribution function? As we mentioned in the previous definition, the CDF as a function of xi is the integral of f of xi dx, f of x dx from negative infinity to xi. This definition is not very strange because it is similar in some sense to what we discussed before regarding discrete random variables, when we mentioned for discrete random variables that f of xi is the summation of f of x for all values of x less than or equal xi. But now, since we have a continuous random variable, so the range of x from its minimum to xi is a continuous range, and hence instead of the summation, the integral operator is used. If we understand this equivalent quite clearly, we can generalize all the discussions that we discussed regarding discrete random variable to continuous random variable with replacing the accumulation or summation operator with the integral operator. And again, this replacement is mainly based on the fact that a discrete random variable had specific discrete values. However, a continuous random variable has all the values in a range or continuous values. Let's try to understand such facts through an example. So let's assume that the current measured through a copper wire is uniformly distributed over the interval from 0 to 20 milliamperes. So this is by definition a continuous random variable because this current can take any value from 0 to 20 without any specification whether these values are integer values or rational values. They are in general any real value from 0 to 20 milliamperes, which leads us to the assumption that that current is a continuous random variable. And here it says that it is uniformly distributed. What is meant by uniform distribution? A uniform distribution, if a random is uniformly distributed, that means that it is equally likely that this random variable takes a value in a certain range, irrespective this range starts from which value to which other value. So if you want to draw the PDF or the probability density function of a uniform distribution, then we have it a constant. So the likelihood that the random variable takes a value in any range, as long as this range is the same, has the difference between the minimum and the maximum identical, so irrespective whether that is between 1 and 2 or 4 and 5 or 7 and 8, the probability will be unchanged. That's why we call it a uniform random variable. So in our example, it says that the current is uniformly distributed from 0 to 20 milliamperes. So we have the PDF plotted as shown, where it is constant over the whole range of our random variable x. Then if we want to find this value, the value of this constant, how will we find it? As we mentioned, the area under the curve represents the probability that the random variable takes a specific range of values. So if you calculate the overall area under the curve, so that means the probability that the random variable takes any value from 0 to 20 or from the overall range, and in this case such a probability is equal to 1. So we can say that the probability that x is between 0 and 20 milliamperes is equal to 1. And as we defined, this probability is the integral of the PDF in the specified range, which is from 0 to 20 ampere. We can write it as 0.02 amperes. And again, this probability is equal to 1. And since we know that this PDF is uniform and hence its value is constant, we can find it easily by solving this equation. And then instead of solving the integral equation, we can calculate the area here simply as the width times the height, where the width is 20 milliamperes and the height is the required PDF. So in this case, we can find that the PDF is equal to 1 over 0.02 for the range from 0 to 20 milliampere, and it is equal to 0 otherwise. It is very important to specify the value of the PDF over the whole range of real numbers. So we specify its value for the possible range of our random variable, and we mention that such density function is equal to 0 otherwise. Now let's see the first requirement. It asks us here to find the CDF and hence compute the probability that a current measurement does not exceed 8 milliampere. Let's start with the CDF calculation. So as we define the CDF, capital F of x, is the probability that our random variable is less than or equal specific value x, small x. If you will get confused between the capital letters and the small letters, let's usually put an index xi. So this probability is equal to the integral of the PDF function in the range where x is less than or equal xi. So in general, that's from negative infinity to xi. However, we know that in this example, the minimum or the least value of x is 0. So we can simply replace this lower limit by 0. And once we calculate this integral, that is the CDF. So let's calculate this integral. So it's an integral of a constant value, and this constant value is 1 over 0.02 as we calculate up here. So we can have it as 1 over 0.02 xi, but this equation is valid for xi in the range of the random variable. So it should be for xi between 0 and 20 milliamperes. What about if xi is larger than this 20 milliamperes? If we recall, the CDF is a non-decreasing function and it saturates at a value equal to 1, because if we, for example, want to calculate the probability that the current is less than or equal 30, it cannot be equal to 30, but since we are calculating the probability in a range less than 30, so such range includes all these possible values, which are all the known values for this current, and the probability of such range is equal to 1. So we can say that the CDF can be calculated as 0.02 xi for the range from 0 to 20 milliamperes, and it is equal to 1 afterwards. And if we want to plot this CDF, we can plot it as follows. In the range from 0 to 20 milliamperes, it follows this equation, which is a straight line equation with a slope of 0.02, such that the value here is 0.02 times 1 over 0.02 times 20 milliamperes, which is 0.02. So the value here is 1. And this is the value at which the CDF saturates. And for values lower than 0, the CDF is equal to 0. So that means the probability that x has any value less than 0 is equal to 0. The probability that x has any value less than, for example, 30 milliamperes, 40 milliamperes, 50 milliamperes, that is a certain probability equals to 1. And the probability that the current is less than any value in this range will be the corresponding value. Again, it makes sense to have linear expression for the CDF, because if we look at the PDF, the CDF is calculated as the area under the curve from the minimum value to a threshold value. So as we increase this threshold value, the area increases linearly because we have such uniform distribution. For the second part of the question, it asks us to compute the probability that a current measurement does not exceed 8 milliamperes. So the question asks for the probability that the current is not larger than 8 milliamperes. So that is less than or equal 8 milliamperes. So this is the CDF at 8 milliamperes, which is equal to 0.008. So we can go up here to at the value of 8 milliamperes and find this value, or by substitution in this general expression that we obtained, replacing xi by 0.008, and then the CDF is obtained. The next requirement is as follows. If it is known that the current exceeds 8 milliampere, so now we have a piece of information. We know that X, the current, is larger than 8 milliamperes. What is the probability that it does not exceed 12 milliamperes? So we want to calculate the probability that the current does not exceed 12 milliamperes, which means it is less than or equal 12 milliamperes. But if we know already that it is larger than 8 milliamperes, so again we have here conditional probability. It is the probability of a certain event given a certain event. Let's call them A and B. As we know from our previous discussion, this is the probability of A intersection B, or the joint probability, divided by the probability of B. Now let's write these two events. So the probability of B is the probability that X is larger than 8 milliamperes. And the joint probability is the probability that X is larger than milliamperes and less than 12 milliamperes. So we can write it as the probability that X is larger than 8 milliamperes and less than or equal 12 milliamperes. And both the values in the numerator and denominator can be calculated based on the CDF. So the probability that our random variable takes a value in the range from 8 milliamperes to 12 milliamperes, it can be calculated as the CDF at 12 milliamperes minus the CDF at 8 milliamperes. Why is that true? Because the CDF at 12 milliamperes means the probability that the random variable is less than 12 milliamperes. However, we want only the range from 8 to 12. Then we can subtract the probability that the random variable is in the range from 0 to 8 milliamperes, which is the CDF at 8 milliamperes. Similarly, for the denominator, it is the probability that X is larger than 8 milliamperes. Actually, this is the complementary event of X is less than 8 milliamperes. So we can say that it is 1 minus the probability that X is less than or equal 8 milliamperes. And again, this probability can be replaced by F, the CDF at 8 milliamperes. From the previous calculation of the CDF, we can have all these values and hence get our solution. Now we will mix our knowledge about continuous random variables with our knowledge about discrete random variables. So it says if the current is measured 10 times, so we made our measurement of the random variable 10 times, then what is the probability that in exactly 4 measurements the current does not exceed 8 milliamperes? So now we have 10 measurements. In some of them, the measurement will be larger than or equal 8 milliampere, and in some of them, the measurement will not exceed 8 milliampere. So what is the probability of this event and what is the probability of this event? These are the events that we just calculated. So the probability that the current does not exceed 8 milliamperes is the probability that X is less than or equal 8 milliamperes. So this is equivalent to CDF at 8 milliamperes. And by definition, this is a complementary function, so its probability is 1 minus F of 8 milliamperes. Okay, this is for any single measurement. So what is the probability that 4 of those measurements achieve this condition? As we solved in a previous example, this is each measurement is independent from the other, so the probability of 10 measurements is the product of the probability of each measurement, and we want to find the probability that exactly 4 measurements achieve this condition. So that will be the probability of such a condition times itself 4 times, or power 4. But this implies that the remaining 6 measurements did not fulfill this condition. So what is the probability that this condition is not fulfilled? This probability is 1 minus f of 8 milliamperes, and this condition occurs for the remaining 6 measurements, so we have power 6. However, still we have a remaining part, which is how many ways are there such that 4 out of the 10 measurements achieve the required condition. Again, this can be solved using counting techniques, because out of those 10 measurements we partition them into 2 groups, or we choose of them 4 into one group which fulfills the condition, and the remaining 6 do not fulfill the condition. So now as if we defined a new random variable, and this new random variable is discrete, its probability is either fail or pass, and passing here is defined as the probability that the measurement does not exceed 8 milliamperes. So out of 10 of these discrete random variables, what is the probability that 4 of them fail or 4 of them succeed in this scenario? It is the probability of success power 4 times the probability of fail power the remaining number of occurrences, multiplied by the number of ways we can have 4 successes out of 10. Of course, we can think of it as the number of ways we can have 6 failures out of 10, but again we know that 10C4 is equivalent to 10C6. The last requirement in this example is to determine the current value that is exceeded in 90% of the measurements. So let's assume that this current value is x naught. So we want to calculate the current value that is exceeded, so as if the probability that the current value is larger than or equal this x naught in 90%. So such a probability is 90%. Again, we know that the probability that a random variable larger than a threshold is 1 minus the probability that this random variable is less than or equal such a threshold, which is equal to 90%. And again, this is 1 minus the CDF at x naught. Again, this is 90%. Then we want to find f of x naught, which is equal to 1 minus 90%, which is 0.1 or 10%. So this is the description of the 10th percentile. However, if we do it step by step as we did here, we have our equations that can be used to get x naught. Again, as we defined earlier, the CDF is calculated as x naught divided by 0.02. So the value that we are looking for, x naught, is 0.1 times 0.02, so that is 2 milliampere. So as a double check, is it really that the probability of the current exceeding 2 milliamperes is equal to 90%? Let's check our CDF, the PDF again. So we had uniform distribution from 0 to 20 milliamperes. So the probability that x exceeds 2 milliamperes is this overall area. And it can be seen clearly that this area is 90% of the overall area, then it is true that the current that is exceeded in 90% of the measurement is the value of 2 milliamperes. Let's solve this example as well. In this example, it says that the total number of hours measured in units of 100 hours, which a certain machine is running over a period of 1 year, is a continuous random variable, and it has the density function as given here. So we have a random variable. Now, since we have already the definition of, or the expression of the PDF, we can use it directly. It asks for the associated cumulative distribution function and some other probability. Let's solve them one by one. So if we want to calculate the CDF, this is a direct application to the relation between the PDF and the CDF. So the CDF is the integral of the PDF from negative infinity to a value x. So we can first check the range of the random variable x. So it ranges from 0 to 2. However, the definition of the PDF has 2 intervals with different definition in each interval. So we can say that the CDF needs to be calculated based on 2 intervals. Let's first draw the PDF. So for x, if we want to calculate f of x, so we have from 0 to 1, we have a linear relation like this, and then a decreasing or another straight line with a negative slope up to the value of 2. As a double check, is this overall area equal to 1? Yes, we can solve it by integration, but here the problem is simple because the area under the curve is the area of a triangle. So we have half the base times the height, which is 1 times 2 times a half, which gives us 1. Then we can tell that this PDF is a true PDF. What about calculating the CDF? For the CDF, we want to calculate the probability that a random variable x is less than any threshold value. As we can see, if our threshold is in this range, so the CDF is equal to this area. And as we increase our threshold value, the area under the curve, the overall area under the curve up to this threshold increase. So we can solve it either using integrations, but we have to be cautious what is the limits of the integral so that we use the proper definition of the PDF, or we can calculate it from the graph. Let's do it through the hard way, which is using the integral expressions. So we can start with determining the range of x. So for x between 0 and 1, the CDF of x is the integral from the minimum value, which is here 0, up to the arbitrary value x. And we put the definition or the expression of f of x, which is here x dx. Usually this is the part which is confusing because we have x inside the integral and x in the limits. However, we can avoid this confusion if we use different symbols. The symbol in the integral limits is the argument of the CDF function, while the symbol inside the integral is the integrand parameter or the parameter of integration. So we can simply replace this parameter by sigma, and then we are integrating with respect to sigma. That change of parameter does not make any difference in the problem. Or another way, if that will be more convincing is to calculate the CDF at an arbitrary value xi, which is calculated as the integration from the minimum value, 0 in this case, to xi for x dx. So this can be simply calculated. This integral is half x squared, and then we substitute by the limits, which gives us half xi squared minus 0. We don't need to write it. So this is the expression of the CDF for the range of x from 0, or the range of xi from 0 to 1. For the range from 1 to 2, the definition is now different. Still, we need to calculate the integral from 0 to xi for f of x. However, for x of I between 1 and 2, f of x has two expressions for its definition. So we have to split this integral into two. The first integral is from 0 to 1 for x dx, and then the second integral from 1 to xi, and in this range the expression of the PDF is 2 minus x dx. The integral of the first part is half x squared. When we substitute with the limits 1 and 0, we get half, and for this part we can calculate it as using any possible method. Let's use the simplest method. It's 2 minus x squared over negative 2, and we substitute by the limits 1 and xi, and we get the integral expression. So this is the CDF for this random variable based on the given PDF. So the most important part here is to make sure that we calculate the CDF for each range of the random variable, which has a different definition for the PDF. The next requirement was to find the probability that a machine is running for at most 150 hours over a period of 1 year. So as if it is asking for the probability that our random variable is at most 150. So that is less than or equal 150. However, in the wording of the problem, it said that the random variable x is defined in units of 100 years. So actually 100 hours, sorry. So actually 150 hours is equivalent to 1.5 as the value of the random variable. So this is simply the CDF when we substitute xi by 1.5. So if we succeed to obtain the CDF in the previous part correctly, then this CDF can be easily obtained. As a double check, this has to be always less than or equal 1. It cannot exceed 1. For the moments of a random variable, as we said before, the moments is a general definition for statistical averages or statistical expectations. So we can have what we define as the mean, mu, and previously we defined it as summation for x times the probability mass function. However, for the continuous case, we have infinite values for x and the continuous range for f of x, so this summation is replaced by integration, and still the integration over all x or over all the range of x. So without loss of generality, we can assume that this integral is from negative infinity to infinity. Similarly, the variance can be defined as sigma squared is equal to the expectations of x minus mu squared And by definition, we said this expectation operator can be replaced by summation in terms of, in case of discrete random variables. However, in case of continuous random variables, it can be replaced by integral. So it's integral, and then we use the argument here, x minus mu squared f of x dx. Again, this variance can be it can be proved that it is equivalent to the expected value of x squared minus mu squared, as we discussed before. If we want to calculate what we call the moment generating function, so it is a function that can be used to calculate the mean and the variance and any other moments. So by definition, the moment generating function m of t is defined as the expected value of e power tx. However, how would we calculate this expected value? This expected value, again, using the general definition of the expectation operator. Expectation, since we are referring to a continuous random variable, then this expectation is calculated via integration, and then this argument is used here, e power tx, multiplied by the probability mass function in case of discrete random variable, or the probability density function in case of continuous random variables. So this is what we call a moment generating function. Since we are integrating over x, then x will not appear after the integral is evaluated, because we integrate and then substitute by all the range of x, and hence we get a function of t. That's why we call it a moment generating function, because for different values of t we can obtain different moments. However, we will leave that for another discussion. Now let's apply this on an example of uniform distribution. As we said, a uniform distribution has a constant PDF over the range of the random variable. So let's assume that we have a random variable distributed according a uniform distribution with a minimum value a and a maximum value b. So this is, if this is the random variable x, so it takes the values from a to b. However, the PDF is constant. So what will be the value of this constant? Again, as we said before, the overall area under the curve should be equal to 1. And here, since the area is an area of a simple rectangle, so we can know that this height is equal to 1 over b minus a, since this width is b minus a. So the PDF in this case is equal to 1 over b minus a. If we want to calculate the mean, so the mean is equal to the integral of x f of x dx. So we can replace s f of x by 1 over b minus a dx, and the limit, which is in general from negative infinity to infinity, here is limited to a to b, since the PDF is defined only in the range from a to b and it is 0 otherwise. This constant can be taken out of the integral, so it's 1 over b minus a, and we have half x squared, and then when we substitute by the upper and lower limits, we get half b squared minus a squared. Again, this value can be decomposed into b minus a times b plus a, and we get the mean is equal to half b plus a. It makes sense because this mean value is right here. This is the median between b and a, so this is the average value of our random variable. Similarly, if we want to calculate the variance, sigma squared, so it is the integral of x minus the mean squared dx times f of x dx. Again, f of x is constant, so it can be taken out of the integral. And we have here a quadratic term, which gives us an integral with a cubic term. By substitution, you can get the variance in terms of, as a function of the upper and lower limits b and a. Let's proceed to this example. The target diameter of a hole drilled in a metal sheet is 12.5 millimeters. So this is the target diameter, the required diameter. However, most random disturbances to the process result in larger diameters. Historical data shows that the distribution of the diameter of the hole drilled, and here the name of such random variable is x, can be modeled by the following PDF. As we can see, the random variable x, which is the actual diameter of the hole drilled, is larger than or equal to 12.5. This is larger than the required or the target diameter. So it is equal to the PDF is obtained via this exponential expression, and it is 0 otherwise, which means it is 0 for values of x less than 12.5. Notice here that the distribution has a constant k, and most probably he will ask about this constant. So let's first start with calculating this constant. How do we calculate this constant? This constant is calculated based on our knowledge that the total probability is equal to 1. So the integral of the PDF over all values of x should be equal to 1. So this integral can be written as integral from 12.5 to infinity for k, which is a constant that can be taken outside the integral. And then we have e power negative 20 times x minus 12.5 dx. So we want to solve this integral equated by 1. Then we have equation in terms of the constant k, and we can consequently obtain the value of this constant k. Obtaining this constant is very easy because this integral is an exponential integral. We can change random variables. We can say that y is equal to x minus 12.5. Then we have the integral is k, and then our x starting from 12.5, then our y starts from 0 up to infinity, and we have e power negative 20y dx is equal to dy. So we have that's equal to 1, and this integral, as we know, is e power negative 20 y over negative 20, substituting with the limits, and eventually we get 1 over 20, that is equal to 1, which means that the constant k is equal to 20. So even without asking explicitly for the value of k, we will need it for further calculations. So we can do our calculation based on the fact that the total probability is equal to 1, which means that the integral of the PDF over the whole range of the PDF should be equal to 1. Then in this example, we know that k is equal to 20. For the first question, he says if a part with a diameter exceeding 12.5 millimeter is scrapped, what proportion of parts is scrapped? So if we select, or if we take all the parts which have diameter exceeding 12.6 and we scrap them, So what is the proportion is scrapped. So this is equivalent to calculating the probability that the diameter is larger than or equal 12.6. So again, this is 1 minus the CDF at 12.6. Then we need to calculate the CDF. So it is good in such examples that we practice calculation of the CDF via integrating the PDF. So our CDF, f of xi, is the integral from the minimum value, which is here 12.5, to xi in general, and then we have k, which can be replaced now by 20 e power negative 20 x minus 12.5 dx. So it can be obtained that this f of xi, this CDF, is equal to, of course, 0 for the range of x less than 12.5, and for the range of x larger than or equal to 12.5, it is 1 minus e power negative 20 x minus 12.5. So this is for x larger or equal 12.5. So if you want to calculate the CDF at 12.6, we just substitute 12.6 here, and then we get the required proportion. The next part of the question asked about the probability that the error in the diameter does not exceed 0.1. So what is the error in the diameter? It is the difference between the actual diameter and the required diameter. So actually we can say that this is the probability that the error in the diameter, so the actual diameter minus the target, does not exceed 0.1, so is less than or equal 0.1. In general, when we calculate the error in the diameter, it should be the absolute error. So if the error does not exceed 0.1, that means that it is the actual diameter is not 0.1 larger than the target or 0.1 lower than the target. So here we have to put it as the probability that the absolute value of x minus 12.5 is less than or equal 0.1, which can be written as the probability that x is between 12.4 and 12.6. However, in this example, we know that in the range from 12.4 to 12.5, there is no probability of such values. So we can simply say that this is the probability that x is between 12.5 and 12.6, or since this is the least value, so this we can say that it is the probability that x is less than 12.6, which is again the CDF at 12.6 that we calculated for the previous part. So again, it is the same requirement that can be asked in many different ways. However, the way or the approach we solve the problem is similar. The last part of the requirements in this problem is to find the expected value of the diameter of the drilled hole. So the expected value, again, this is another expression for the mean or the average. So it is the expected value of x or the mean. So it is calculated as the integral of x f of x dx. So that's why, again, we needed to find the constant k in order to be able to make such calculate such integrals. So we have 20 integral from 12.5 to infinity. This is the overall range for x e power negative 20 x minus 12.5 dx. This expression or this integral can be solved by parts, and then once solved by parts, we substitute by the upper and the lower limits to get the exact value of them. In this example, it says that suppose the cumulative distribution function, the CDF, of the time until a chemical reaction is complete, and he defines the units in milliseconds, can be approximated by this value. So again, we have 0 in a certain range, and then a certain value in the other range. And he asks about proportion of reactions that is complete within 100 and 200 milliseconds, and the mean time for the reaction to be completed. We are given here directly the CDF. So if we want to calculate the proportion of reactions that is completed within 100 to 200 milliseconds, so this is the probability that x is between 100 and 200 milliseconds. So this is CDF at 200 minus CDF at 100, and both of them can be obtained directly from this expression. So that will be 1 minus e power negative 0.01 times 200, so this is negative 2, minus 1 minus e power negative 1. So this is the first part, and it is very simple and easy to calculate. And then for the next requirement, he asks for the mean time for the reaction. So the mean time, or the expected time, or the average time, then we need to calculate the mean or the expected value of x. So in order to do this, we need to calculate the integral of x fx dx, where f of x is the PDF. However, we don't have the PDF. How can we obtain the PDF from the CDF? We knew before that the CDF is the integral of the PDF. The reverse relation will be, as we can expect, a differentiation function. So we can say that the PDF is the derivative of the cumulative distribution function with respect to x. So again, the differentiation here is very straightforward. So we get 0.01 e power negative 0.01 x. So this is the PDF, and again, we must specify the range of the validity of this PDF. So this PDF is valid for x larger than or equal 0. Otherwise, the PDF is equal to 0. So that when we calculate the integral here, it's integral from 0 to infinity for 0.01 x e power negative 0.01 x dx. And again, this integral can be calculated by parts to get the required mean time. Our last example is about calculation of expected values as well. So he says here a continuous random variable has the following PDF, and we have the PDF. Again, it's exponential in the positive range of the random variable and 0 otherwise. And he asks us to find the mean of a random variable, a new random variable defined as a function of x as e power 2x over 3. So we can calculate the required mean. Again, it is, if we want to calculate the expected value of gx, so by definition it is the integral of g of x times the CDF dx, and we can substitute g of x here by the given expression. So it is e power 2 over 3x, while f of x is e power negative x dx, and this is valid only in the positive range. So the limits of integral are from 0 to infinity. Here we have a very simple exponential integrand, so the integration can be solved directly, and we substitute by the limits from 0 to infinity to get the required mean.